Well, thanks a lot for coming again. So yeah, we'll just have the same rules as last time. Yeah, if you have any questions, please ask. And yeah, we'll have a short break halfway. Is it possible to have the volume a bit down? Because it's very loud, thank you. Yeah, so I committed already the worst thing you can do, which is start writing before the thing starts. But I hope that you will benefit from my beautiful handwriting, which I cannot really do during the thing. So I wanted to quickly recall some things, which are basically the building blocks for today. So for the FKG inequality, it's often constructed via this FKG lattice condition. And this FKG lattice condition is quite easy to work with, for example, because if you take the product of two functions like x, clearly they still satisfy this condition, which makes it nice. There's this tower property, which means that if you have constructed a measure on one space which has FKG, and this measure, yeah, the points in this space kind of work as a conditional measure for another space, then the whole thing works nicely. So this allows us to establish the FKG inequality on bigger spaces. And then what we did after that was that we said, okay, we have the hexagonal lattice. And we look at measures on which assign a real value to the vertices of this lattice, probability measures. And we quickly wrote down a number of properties, and we show that if you have those properties, then the measures nicely converge. So we say that here we look at all the finite subsets of the lattice. So you can really think about, okay, we put boundary conditions outside of lambda, and then we define a model within the finite domain lambda. So for example, you can think of the Ising model, but we particularly looked at the height function. Then we say it's monotone if increasing the domain stochastically increases your measure. Well, we call it tight if, well, when you take lambda larger, your values don't fly away, basically. We have this boundary Markov property, which is the following. If lambda has the connected component decomposition lambda n, right? So lambda is kind of like a union of domains which are not connected. Then we want that the restriction of mu lambda to lambda, this is just the product of the restrictions to the different domains. And this is really a bit weaker than having a real Markov property. It's really only under certain boundary conditions. And you have shift invariant. What does that mean? It just means if I have a shift theta, then mu theta lambda, this is just mu lambda, but all samples shifted by theta. Okay? So a prototypical example is the following. You take the Ising model with minus boundary conditions. Then you fix a domain, lambda, you put minus boundary conditions outside, but within the domain you can do whatever you want. And then monotonicity is easily checked because you satisfy this FKG inequality. And if you look in a smaller domain, it's just like conditioning the values on the complement to also be 0, right? So if I compare a measure on some domain delta, and I want to compare it to the domain lambda, okay, both already have minuses outside, but to get the measure in lambda, I'm just conditioning that I also have minuses here. And remember, with the FKG inequality, when I condition on a decreasing event, I'm always decreasing stochastically the measure. This is almost the definition. Okay? Now, this is all very measure theory-like. I mean, what was the main result? The main result was basically if we have this, then we have convergence in the local topology to ergodic measure. So this is all very measure theory-like. I mean, we didn't really use the graph structure anywhere. But the two main results that we proved, which are very classical, are the following. So it's the Burton-Keen. And the Burton-Keen argument says that if I have a percolation, if I have an ergodic percolation with insertion tolerance, then the number of infinite connected components belongs to 0, 1. Okay, of course, this is not really a random variable by ergodicity, it's just constant. And what was the second thing? So this is the non-coexistence. Yeah. If omega is an ergodic percolation, then it is impossible that there exists a unique infinite component. There exists a unique infinite component for complement. And the measure has FKG. Okay. So we spent a lot of time on these things. Those results, of course, they rely on the geometry of the graph. This on the amenability of the graph, and this one on the fact that it's really planar in 2D. And today we're gonna, we're gonna sort of put all these ingredients together to show that we have delocalization for this thing. So in fact, for example, the non-existence theorem, I think we're going to apply it maybe 3 times. So it's nice to, I think, review this in detail. So we fix beta, and we've defined for a finite subset of the set of vertices the following measure on H. So we always consider measures on this set. We define this to be equal to 1 over partition function times the indicator that the support of H is in lambda times e to the minus beta times the square of the height differences. Okay? And what we're going to prove, so that's the main theorem, that if beta is smaller than log 2, then this variance blows up. Okay. So before anything, I think it's important to quickly make some observations about this model because it's quite a simple model and it has some very basic features. So first, for example, there's a flip symmetry. So obviously H and minus H, they have the same distribution. Okay, I mean, it's just the Hamiltonian is invariant under replacing h by minus h, so clearly this is true. There's also the gradient property. I mean, we just, yeah, this we also call the Hamiltonian. So the Hamiltonian depends only on the gradient. Okay? So I mean, here we kind of impose zero boundary conditions because we say, okay, the support of h has to be in lambda, right? So outside of lambda it has to be 0. But if we lift everything, we say, okay, boundary conditions are 1. It's just like adding 1 to the height function, right? The FKG inequality. So the FKG inequality is very easy to see because, well, we have a bunch of vectors and we can just check the FKG inequality for each vector. For this vector, it's obvious that you satisfy the FKG inequality. And then if I fix x, y, then it's also obvious here that I satisfy the FKG inequality. Why is that? Because suppose I take two height functions. So now if I look, okay, I need to compare these terms. So if I look at omega maximum with eta, I'm looking at the height difference between those two squared. And then for the minimum, I'm looking at the height difference between those two squared. But this is of course always going to be smaller than if I take the difference between the yellow one squared and the difference between the red one squared. Okay? So this is quite a general thing that if here I put a convex function of the difference, I'm always going to have a lower energy when I look at the maximum or the minimum. And then if I take e to the minus convex function blah blah blah, it's good. And then if I take a product of that, it's still good. So it's really trivial here that we have the FKG inequality. And the final thing is the Markov property. So what does it say in this case? It says that mu of lambda, if I condition on what happens on the boundary of some other domain, then in this conditional measure, what happens in the domain, this is kind of orthogonal, so independent of what happens outside. Okay. So you can imagine that we have, well, this is lambda. Oh. And then we have some smaller domain which is called delta. Then if I condition on what happens exactly outside of delta, then the inside and the outside become independent. And this is actually also easy to see from the Hamiltonian because every term in the Hamiltonian, no term in the Hamiltonian can contain both a vertex outside of delta and one inside of delta, except if you're on the boundary. But then we already fixed its value, right? So here you have to set the boundary of delta, and there's no edge which clearly contains something in delta and something outside of the closure of delta, right? So are there any questions about this? Okay, so I mean, clearly this is a nice framework to start. But there's one problem because, well, what we would like is clearly to have this monotonicity in domains. But clearly this cannot be true because if I look at what happens here within delta, right, I consider now two domains, delta and lambda. if I look at what happens here in delta, then I know that everything outside of delta is 0. Right, by definition. If I consider mu delta, then outside of delta, everything is equal to 0. But now if I look at mu lambda, those 0 values that are here, they can be both positive and negative. Right, so when I'm taking my boundary conditions further away, I'm sort of allowing the model to fluctuate more in both directions. And fundamentally, it would be very strange if somehow we have some monotonicity in the domain. And yeah, a different way of phrasing the same thing. I mean, in the Ising model, what we said is, okay, we just condition everything on being minus outside of delta, because minus is the smallest value. But clearly you cannot do that here because z doesn't have a smallest value, right? We cannot say, okay, we just condition on the smallest value in z and then condition. Okay, so mu lambda is not monotone in lambda. Okay. So I already said it a little bit last time, but we're gonna write h in a different way. H is the random height function. So h, we're gonna write it as sigma times the absolute value of h. Okay? And we shall see that in fact we can recover a lot of this framework by looking at the absolute value of h. So let's first rewrite the value of the Hamiltonian. So hy minus hx. This is equal to minus sigma x sigma y times hx hy plus, yeah, there's a 2 here, I think, no? Yeah. Sorry? Here? Ah, yes, thank you. Yeah. So we obviously have this inequality. Equality. Yeah, and now everything is measurable with respect to the absolute value. So in this way, we can write this vector. We can write it as e to the minus beta times the product over the heights squared. We can write this as okay. Yeah, I mean, we can first kind of pull out those things, and then we look at these vectors. So we take the product over the edges, and we get e to the minus beta h y squared e to the minus beta hx squared. Then we get e to the beta times the sum over all the edges times sigma x sigma y hx hy. Okay, so we're just really, yeah, well, we just have a product of those things, we separate a little bit, and that's it. Now suppose we want to calculate this number. So we want to calculate the probability that the absolute value of h is equal to some zeta. right? So, okay, I want to forget a little bit about this normalization constant. Then, of course, what I need to do is to sum this quantity over all the possible h's, right? Because this gives me the relative probability of a certain h, but now I'm looking at more h's which can contribute. So of course at each spin I can assign a plus or a minus, and it gives me a different thing except if zeta is 0, because if zeta is 0 then plus 0 is minus 0. So I just want to correct for that. Then I observe that those factors in fact don't depend on sigma, they only depend on the absolute value. So we get product xy e of lambda e to the minus beta hy squared e to the minus beta hx squared. And now I'm really going to sum over all the sigmas, right? Because I need to sum over the sigmas, and this is the only term which depends on the sigmas. So we get sum over sigma so it's only in lambda. And then we get e to the beta sigma x, sigma y, hx, hy. Okay, I interchanged here the betas and the zetas and the h's, but we can think of them as being h's. This we can also write as the partition function of the Ising model. Right, so here we're really just looking at z Ising of j, so j depends on zeta. And of course, okay, here we almost have the expression for j, so what are the coupling constants of this model? It's just 2 beta zeta x zeta y. So now I claim that every factor satisfies the FKG lattice condition. So for this factor, okay, it's not in zeta, right? So the thing here is the whole thing depends on zeta. This thing clearly depends, yeah, well, here you can just check that in fact you have equality because you're just counting zeros, so you're just saying something like the cardinality of the union plus cardinality of intersection is the sum of the cardinalities. Here you have a lot of factors, but every factor only depends on one vertex at a time. And if you depend on one vertex at a time, then also you're going to have the FKG lattice inequality with equality, right? So this factor is also trivial. So finally, we need to show that we also have the FKG lattice condition for this Ising model partition function. So what we need to show is the following. Okay. So we take two positive functions and we compare, okay, what is this partition function if we take the minimum and the maximum and we compare it to the ones where you just take them separately. Okay? So in fact, what you can see is that, well, those coupling constants, they are clearly increasing in the value of zeta. If zeta is bigger, then those coupling constants are also bigger. So there's like a smallest one, which is here, right? When you take the minimum, you get the smallest coupling constants. And in fact, what you can show is that you can write this as A. You can write this coupling constant, you can write it as A plus B. And you can write this one as A plus C. Right, so those are non-negative functions on the edges, which are the coupling constants. Okay, and it turns out that you can write this one as A plus B plus C plus D, where they're all non-negative, right? So another way of saying is that this one is the smallest. And if I sum those coupling constant and those, it's going to be bigger than those plus those. Right, it's again, if you want, again an FKG lattice type inequality. And now what we can do, we can use, in fact, the Griffiths inequalities that we used last time. Because last time what we deduced is the following, namely that Z of A is increasing in A. Right? It's increasing in A because of the first Griffiths inequality. And then we get ZA plus B plus C plus D is greater or equal than, well, we just ignore the D. So it's bigger than A plus B plus C. And then we know that Z of A plus B plus C times Z of A is bigger than Z of A plus B times A plus C. And this, well, you can check, but this is what we proved last time, and this is the second Griffiths inequality. So remember that we proved two Griffiths inequalities. The first one was true because we have this coupling with percolation. And we could rewrite certain correlation functions as the probability of an event. So in fact there we didn't even use FKG, but just this coupling. And for the second Griffiths inequality, we proved that in this percolation measure certain events have FKG. And this allows you to get the second Griffiths inequality. But if you use them together, then you can prove this FKG lattice condition. So in fact this this method where you look at the Ising partition function appears as a weight, and this is not the only situation where it appears. So for example, if you look at the loop O2 model, you can also do it. In the XY model, there's also a way in which you can do it, right? So okay, not via this way, but if you really look at the XY directly. Yeah. Now is the question, what do I erase? But I'm going to erase here. Okay. So, lemma. H absolute satisfies FKG in mu of lambda. So this is what we just proved, right? Because the probability mass function satisfies this FKG lattice condition, and therefore we are done. And now corollary. the law of h absolute is increasing in the measure mu lambda is increasing in lambda. So proof. Well, mu of okay, let's take lambda is smaller than delta. Then mu of lambda is equal to mu of delta, conditional on the event that h is equal to 0 on delta minus lambda. This is the same thing that we do all the time. But actually it's not always the case that if you condition on an event like this, it's a decreasing event for this, right? But if we know that h is equal to 0, it's equivalent to asking that the absolute value is equal to 0. Right, so even if you look at the marginal of this measure on the absolute value, this is a decreasing event. So it's important that we have a measure on height functions, but here we're really dealing with the marginal measure. For example, if we put a 1 here, then we're not conditioning on something that is kind of measurable with respect to this with respect to this thing. And also we're using here, of course, the fact that this set has the smallest number. Yes.
I was wondering, how much do you use the Gaussian structure to have this absolute value FKG? If you have other type of interaction, it's not quadratic, you can extract still something? Or?
Yes. So it's a very good question if we can replace the quadratic thing by something else, and the answer is yes. What is nice in this proof is that just this, things decouple very nicely. This term only depends on one vertex at a time. But in general, you can cover potentials which satisfy a condition. So basically it's V, it has to be convex, symmetric, and the second derivative has to be, I think, decreasing. Over the positive numbers. Okay? So, okay, it's just a definition. But if you, here we took V equals to the square of the height difference, but now you replace it by V of something, V of the height difference. Now if V is a convex symmetric function and the second derivative is decreasing over the positives, then you also have this, okay? Basically what happens is that here you still get the Ising interaction term, so there's all good. Those terms are going to depend on both x and y at the same time. So there's another condition to check that you satisfy this FKG lattice. But here you can do it. And basically what's nice is that if V is the square, then obviously the second derivative is constant, so you're all good. But for example, if you replace the square by the absolute, then you're also still good. Because, well, if you're the absolute function, then here the derivative is strictly positive, and there it's 0. So you're decreasing still over the non-negatives. And so this kind of works for all potentials which are in between the two. Like if you want. Thank you.
So, from point of physical intuition, those conditions would mean that we have a unique, well, degenerate ground state, but well, a state of, say, which occupies the minimum of the potential. However, it's for convex and symmetric, but what is possible physical intuition for the third condition?
Okay, I mean, I think this would be a bit too difficult to explain. I don't know if there's a good physical explanation. But for example, if you take uniformly random Lipschitz functions, so for example, you look at one Lipschitz, then you don't satisfy this constraint because then the potential looks like this. So then clearly here the second derivative is 0. And, well, here it's infinity. It turns out that in that case, there's another absolute value fkg, but it's a little bit different. So, yeah, well, I can just say it, but in that case, you can show that this function satisfies fkg. Okay, so you have to shift, but it's a bit of a different story. And I don't know how physical it is, this particular condition.
But we need this condition, well, some condition, some third condition in order to guarantee fkg.
I don't understand, sorry.
So basically we need fkg and okay.
I mean, the fkg always works, the fkg for the height function. That is what we established here. And the absolute value fkg, this one is a bit trickier to obtain. Yeah. Okay, just as a side remark, this fkg is also true, for example, for the 6-vertex model. So like it's really a more general concept. Yeah. So what do we get? In fact, as another corollary, we know that if we look at the variance of a point is increasing in lambda. Right now it's simple. I mean, yeah, we have that. In fact, the whole law is increasing in lambda. So obviously, if we look at the variance, which is an increasing function of the absolute value, then this is also increasing. And in fact, yeah. So now, as step 1, the goal is to prove. Actually, I'll do it in a different color. So the first goal, what we're trying to prove, is the following. Is this readable or not? Yeah?
In red it's not very good.
Sorry?
In red it's not very good.
It's not very good?
I think.
So in step 1, our goal is to prove that, first of all, you have this, that you're increasing in lambda. And this, of course, we have now done. Okay, so this is okay. And in the second step, in the second part of the first step, we want to prove that if you're localized, then in fact, as lambda goes to infinity, you can take some limit. And this limit is ergodic, flip symmetric, and has FKG. Okay? So at this point, this second part of the step 1 is completely unclear. But okay, we proved this first thing. But now for the second part, we can assume localization. And what does localization give us in this case? Well, localization kind of gives us the tightness, right? Because by definition, if you're localized, then this is finite. And therefore, even if you take the supremum over lambda, this thing is going to be finite. And if you have finite variance, well, then, yeah, you have this tightness. So if we look at the absolute value, we satisfy the monotonicity. We satisfy the tightness by assumption, right? Because we want to, prove that it's delocalized, so we assume that it's localized. The boundary Markov is also good. It's just because by definition, we're only saying, okay, if the boundary condition decomposes as a union of different things, then things are independent, and this is kind of baked into the model, right? Actually, we don't have all the information here if we see the absolute value, but we just don't care. The only thing we're saying is, if my domain splits up, then I have independent things. And the shift in variance is of course true because it's just a symmetry of the model which we're never really kind of breaking. Okay? So another corollary, if localized, then the law of H in u lambda converges to something ergodic as lambda goes to infinity. Okay? So now to get, and of course this limit also has the FKG inequality, but this is not even so important at this stage. So we've now proved that the absolute value converges. And now the question is, of course, how do we add back the spins? Right, so how do we encode the spins into this model? So suppose we have a finite domain. So in mu lambda, conditional on the event that the absolute value is equal to zeta. Sigma is an Ising model with couplings J of zeta. And remember that the coupling was just equal to 2 beta zeta x zeta y. So remember that we had this coupling with the FK percolation, where conditional on the FK percolation, the signs were in fact just a random assignment of coin flips to the connected components. Right, so remember that if we had a graph and some of the edges were open, then we could just flip a coin for each connected component. Right, so we have one connected component here, one there, and one there. And then when we flip the coins, maybe it's just something like that. So first, we recall that if we look at this percolation, that this percolation has FKG. So this is what we used, for example, to prove the second Griffiths inequality. Notice also that P edge of J is increasing in J. So this is not so hard to see because basically what happens is that if you increase the J, then the probability of that edge, sort of the weight of that edge being open increases. So this is good for you. And then because you satisfy the FKG inequality, because this one is more likely to be open, the other ones are also more likely to be open. Okay? So I don't want to give a proof of this now, but this is straightforward to prove. So now we can use the tower property, right? Because, sorry. Yes, so at this point we know that if we only look at the distribution of the absolute value, this converges. But even to know that this converges, it's not yet clear, because the signs could make us not converge somehow, right? We're not trying to converge subsequentially, but we're really trying to converge.
But now you're trying to make the original measure converge, or the measure for the absolute value?
So we proved already that the absolute value converges, and our next objective is to prove that actually the actual measure converges. And also that this limit is ergodic. Because it would even be possible that it converges, but that it's somehow not ergodic.
But we have FKG for H.
Exactly. So actually we're going to prove this.
Okay.
Right? And then we say, but FKG is just preserved in the limit. So in this step one, actually the FKG for the actual height function really doesn't play a role. Yeah. So just to recap, we know the absolute value converges, And we now want to show what happens with the spins. And we are going to understand the spins via this percolation. And yeah, we just recall that we have this structure that, okay, when you have the percolation, then conditional on the percolation, the picture looks like this. Yeah. So conditional on the absolute value, we have an Ising model. And the edges in this Ising model, they have FKG. And if we increase our coupling constants, they're also going to be more, yeah, then you have stochastic, you're stochastically increasing the edges. It's just saying, okay, if the coupling constants are stronger, then spins are more likely to agree. So hence, by Tower property, H omega has FKG. And is increasing in lambda. Okay. Sorry. So omega are the edges. So omega belongs to 0, 1 to the edge set, and there are the open edges. Right, so for example here omega is contains those two edges. Okay. So here we really see that in fact this Tower property is really a useful property, because a priori it would be very difficult to establish, for example, that omega satisfy the FKG inequality. And there are, for example, instances, I don't know if I didn't check it for this, but where you have kind of another thing, where first you have here something which satisfies FKG lattice, and then you prove that the pair satisfies FKG inequality. But you are certain, you also can see that the FKG lattice condition is actually false. So the FKG inequality is really a sort of stronger thing than the FKG lattice. And sometimes you really need both tools to establish the FKG inequality for more complex objects. Okay? Yeah, I want to mention that I'm cheating a little bit here because, of course, to properly define omega, you need to have some external randomness in your measure. But I don't want to worry about this too much. But let's put it tilde. So I'm just saying, okay, yeah, at every edge you need to sample a random variable to define this, but it's not really a problem. Okay. Hence, just by the 4 properties that we wrote down there, we can check that they're all satisfied. So the law of this pair converges as lambda goes to infinity. Right, so we're simultaneously tracing now the absolute values which are increasing and their correlations. And if we look at this joint pair, this is going to converge as lambda goes to infinity. So clearly here the tightness is just the same tightness as before. Here, okay, it's just 0, 1, so it's trivial that you have subsequential convergence. To some ergodic limit mu tilde. Right, so mu tilde is this measure where you can see the absolute value and the thing. And it's ergodic, but it also satisfies FKG inequality, and it also has shift invariance. So now it's kind of funny because we have a collection of absolute values and a collection of percolation clusters. Right, so maybe here the absolute value is equal to 6, 4, 2, 3. Then you have another cluster, maybe it's -2, -1, -5. Oh, yeah, so I was already cheating a bit. Because, well, we said that conditional on the percolation, you just need to sample like a coin flip to decide on the actual height. And here I also flip those coins, right? So here I'm looking at this measure mu tilde, where in principle I see the absolute values and the percolations. And then to get the measure, I need to flip the coins. But actually this is not exactly the case, right? Because there may be infinite connected components. How do we deal with infinite connected components? Now there are actually 3 options. We're ergodic, right? So it's possible that there are no infinite connected components. Then I can just flip the coins and we're going to be happy. We're going to see that in a second. Or there's one infinite connected component. And this is actually really bad because if you have one infinite connected component, you can flip the coin. But this breaks the ergodicity, right? We wanted that this measure, this limit is ergodic. But if I now flip one coin to decide the sign of the infinite cluster, this means that either I'm going to have more than 50%, which is strictly positive, or more than 50%, which is kind of negative. Right? So if I have an infinite connected component, this is bad for us. And it's also possible that you have multiple infinite connected components, and then it's not even clear if this measure is going to converge, right? Because if you have an infinite connected component, should they have the same sign or not? So can I flip the coins independently, yes or no? Yeah, these questions are hard to answer. So at this point, we just lack the information of the coin flips. And we see that actually to answer this question, we must say something about the possible behaviors of omega. So what can we say? So first of all, by Bird and Keen, the number of infinite components is less or equal than 1. So why is the number of infinite connected components less or equal than 1? We have to prove insertion tolerance. But insertion tolerance is kind of easy to see directly from the model because when you look at the Hamiltonian, if you condition on what happens outside of a box, then still everything within the box is still possible. And this kind of allows me to see that, if I condition on what happens outside of a box, I can always close the box. And you can also consider the dual percolation. So the dual percolation, if I have a percolation on a graph like this, then the dual percolation is sort of the complement, but on the dual graph. And by Bird and Keen, you can also prove that the number of dual infinite components, this is also less or equal than 1. Okay? So again, by the same strategy, you can see, okay, if I condition outside of the box, the heights can still take all the values you want. And this allows me with a positive probability to open or close the edges I want. Okay. Finally, omega satisfies FKG. So by non-coexistence, I have the following. Omega percolates implies omega dagger does not percolate. So if I'm able to say that one percolates, at least I know the other one doesn't percolate. Yeah, so we're going to take a little break, and after the break we're going to prove that this implication actually implies that you are delocalized, right? So we want to show that actually omega doesn't percolate, because if it doesn't percolate, it's really the best for us with this coin flip business. And to rule out that it does percolate, we're going to use this to see that you have delocalization. So we resume at 3:07. Thank you. Okay, so let's restart. So at this point what we did is we said we have the absolute value, this converges. We have the percolation, which carries somehow the correlations between the spins. And this pair converges. And then if we see the configuration in the limit, to get the spins we just need to sample the coins. And at this point we also know that, well, there's at most one infinite component for this percolation. And if it percolates, the complement, the dual complement does not percolate. So what that means geometrically is that, well, if omega percolates, let's say have a connection to infinity, then the complement doesn't percolate. And that means that every point is sort of surrounded by bigger and bigger circles. So now what we want to prove is the following. If omega percolates, then what happens? Then actually delocalization. Delocalization. So this is of course a contradiction. Okay? So let's say that we fix now a vertex x. We assume localization, we assume that this measure exists. We also assume that omega percolates. And we want to show that the variance blows up. Now what you can do is that you can run an exploration process. So what you do is the following. You start exploring outside a very large box. So maybe you start exploring here. And you sort of want to show that this variance is large. And okay, maybe we can't do that, but maybe we can find some other piece of information. So what we're going to do is we're going to explore the largest omega connected circuit, right? So you have here this dual complement, right? You have this percolation, which is omega dagger. And you follow where it goes, but you know that it cannot go in the yellow stuff. So when you finish this exploration process, what you see is that you have discovered a sort of contour of yellow, and everything inside this contour is kind of unknown. Right, so in fact, what the picture looks like is something more like this. Okay. So now you can ask, what does this conditional measure look like? So let's call this circuit, let's call it gamma. So on gamma, we know first of all that omega is open. So it means that all the vertices on this circuit have the same sign. And second of all, what we also know is that the absolute value of h is at least 1. So why is it at least 1? Because the coupling constant of each edge was the product of the absolute value. Right? So if the absolute value is 0, then the coupling constant is equal to 0, and all the edges are closed. So there are two options. So with probability 1 over 2, h on gamma is bigger than 1, or with probability 1 over 2, h of gamma is smaller than minus 1. Okay? I mean, here we're just saying the sign is the same, and the absolute value is at least 1. But after flipping this coin, you have a Markov property. You know everything about the model. We're really using the Markov property for the heights. Right? So we really know everything except the sign, but we don't care about the sign. So now if gamma, I'm just gonna use this for the interior of gamma. Then the variance of mu, the variance of hx, this is going to be something like you integrate over the location of gamma, and you look at the height function on gamma, and then you get mu height function, where this is on the interior of gamma, with boundary condition h. So this is a boundary condition. This is just a simple conditional expectation. And now, in fact, what you can easily show is that, in fact, this quantity, this is greater or equal than mu gamma interior 1 height hx squared. Okay. So this is just sort of a law of total probability. And then what we're saying is the following. I compare two boundary conditions. One where my height function is 1 or bigger than 1, right? So it may also be bigger than 1. And then I say if I lower it to the height 1, then I'm decreasing the expectation of the square. So this is greater or equal than mu of gamma 0, 1, height hx squared d mu gamma h. But now we can use the gradient property, right? We know that h is flip symmetric. And therefore, if I calculate this, now it's flip symmetric around 1. Right? So what I can do, I can just write this variance, or this square. This is just going to be 1 plus, if I put it at 0.
can be equal to 0. Why can't it be equal to 0, h?
Where exactly? Here.
Yeah.
So it cannot be equal to 0 because we know that it's omega open.
Okay.
And that means also that the coupling constants have to be strictly positive, because if the coupling constants are 0, in this percolation you're always going to be closed.
Okay. And then I have another problem. Before, when you say when you use the non-coexistence,
Yeah.
you use the duality.
Yeah.
But with h equal to 0, does it mean you remove some edges?
Yeah, exactly. So you use the Berezinsky.
You have something completely.
Sorry?
It's not a problem to have h equals 0 and.
Yeah, so you prove the insertion tolerance for omega and omega dagger. Now to prove the insertion tolerance for omega, you're saying like, okay, I see some edges outside of a box, and now I want to show that I can actually open all the edges in the box. But we have this precise Markov property for h, and this tells us that even if I see what all the edges are doing, I can just make all the heights in the box very large and positive. And then you have a good probability of connecting. For the second one, to show that you have insertion tolerance for omega dagger, you can say, okay, conditional on my percolation, actually I can set all my heights to 0. And if my heights are 0, then I'm guaranteed that those edges don't connect.
But for the non-coexistence,
Yeah.
the fact that you have some h equals 0, isn't it a problem?
So at this point, we're not really using h anymore, because we're just using, the only inputs that we're using is, there's at most one infinite component, and there's at most one infinite connected component for the dual, and that the measure is FKG. So for the application of non-coexistence, the insertion tolerance doesn't play a role anymore.
Okay.
I don't know if it, if it makes it clear, but okay. Is it clear now? Okay.
So yeah, just to be sure, if you have h equal to 0, all the surrounding edges are closed. Right?
Exactly.
Okay.
Yeah. So the edges are closed because the coupling constants are going to be equal to 0. Yeah. So if you have a symmetric random variable, if A is a symmetric random variable, then the expectation of 1 plus the thing squared, this is just 1 plus the expectation of A squared. And we're just using that fact kind of here. Okay?
How do you choose this gamma?
Yeah, so I'm cheating a very small bit here. But how do we choose it? Well, we start outside of an extremely large box, and then we find the biggest contour. So this contour exists with high probability. So if you choose your box further and further away, then you will find the contour. And yeah, so this allows you basically to see that the variance blows up. Because this, if you start from very far away, then you're going to find that gamma interior is also an extremely large set. So this value is in fact, this value is approximately equal to the same supremum that you were looking for in the first place. So this is approximately sub lambda, or rather mu of hx squared. Right? So you're kind of proving the following inequality. You prove that the variance of hx is larger than 1 plus the variance of hx.
Yeah, but I don't understand how you build this gamma even choosing this.
Okay. Right. Maybe it makes more sense if I give like the complete proof and then. We define v lambda to be the variance in the box lambda, and this value is increasing in lambda. So we want to show something about this, and what we want to show for all lambda, for all epsilon bigger than 0, there exists a delta such that v of delta is bigger than 1 minus epsilon v of lambda plus 1. Okay? So I mean, these are non-negative numbers, and we want to show that the supremum is infinity. And well, if you satisfy this, then clearly the supremum is infinity. Okay? So we fix lambda and we fix epsilon. And now we choose delta so large that the connection probability is at least 1 minus epsilon. So yeah, we want to show this. Choose, so fix lambda and epsilon. Choose delta so large that the probability that you connect, so this is lambda delta, is smaller than epsilon. Okay? Okay. So now we call this event. So we call this event A complement. So that means that A is the event which has probability at least 1 minus epsilon. So now the variance in mu of hx, this is going to be clearly at least, well, we can just only integrate this square over A. So it's the integral over A of d mu of gamma h of mu gamma interior h of, so let's call it h tilde, hx squared. Okay. So what I'm saying here is the following. I explore my my shape from the outside, and now with the probability 1 minus epsilon, I'm going to find this gamma circuit. So now by the domination we just did, this is going to be mu of gamma of 1 this is equal to integrate over A 1 plus mu gamma 0 hx squared. And now we are done because this is just V gamma 0. And V gamma 0 is bigger than V lambda. And therefore this is at least 1 plus V lambda times mu of A, which is at least 1 plus V lambda 1 minus epsilon. So I mean, in the end, with explorations, you cannot explore the outermost circuit because there are infinitely many. You need to sort of choose where you start the exploration for this to make sense. But then if you do a small analytic argument, you can see that it works. So I hope that this clarifies. Okay. So now we have proved that if we have localization, then omega cannot percolate, because percolation led to localization. Okay, so it doesn't percolate, and it means that we have this measure which consists of, you have the absolute heights, so maybe it's 3, 4, some are connected, some are not connected. And to go from mu tilde to mu, you need to flip coins. Right? Because in order to get the signs of the clusters, you need to flip the coins. But now what's really nice is that, in fact, this measure is ergodic. So, I mean, you need to show that when you flip the coins, you're not losing the ergodicity. But what you can look at is the following measure. You just put a side percolation measure with parameter 1/2 at the sides. Right? So at each side, you're just going to flip a coin. And this product measure is also ergodic, right? So if you multiply by a side percolation measure, you're going to still be ergodic. And now, what is the sign of sigma? Sigma of x. So now I look at some vertex x. So here what do I have? I have a height function with the absolute value. We have omega and we have the coins. This is going to be the coin of the vertex which depends on omega and x. And v of omega of x is the vertex in the omega connected component of x with the lowest dictionary order. Okay. So what this means is that I somehow need to choose the spins in an ergodic way, and I want to see that it's ergodic in a simple way. So now what I do is I flip a coin for all the sides. So maybe it's plus, minus, plus, minus, plus. And now for each vertex, I look at the lowest vertex in the dictionary order. So in this case, maybe I'm going to look here. And I say, I have a minus. So this one is going to get a minus. So this is good for two reasons. Clearly, every vertex in the same connected component will have the same spin. The spins are independent. But I'm not making any global choice. Right? All the choice comes from this local information in this side percolation measure. If, for example, I had said, we just flip a coin for every connected component, if there would be an infinite connected component, I'm actually introducing some global information, but this is here not the case. So hence, hence H is ergodic in mu, right? So I really construct my measure mu out of this pair. So are there any questions about this construction? Yes, yeah. So what you do is that you say, well, in finite volume, I can flip the coins. And now, like in the limit, you can see that this also, this property is preserved. So if there were infinite connected components for omega, it would not be so easy that you could do this coin flip in this way. But since all the components are finite, you can see that, the heights are really filled in by just flipping the coins. Okay. So now we know that mu lambda converges to mu, and it's ergodic FKG flip symmetric. Actually, it also satisfies the Markov property. It's easy to see that this is also preserved. That's it. Okay. So now we want to look at mu. And we know that, in the end, we're going to get the contradiction from the flip symmetry. So first what I want to do is to very quickly derive two lemmas and then see, how this is sort of going to lead to the proof. So first of all, the first lemma, I mean, it's a proof, but in the end, we're not going to really use it in the real thing, but it's just to illustrate the strategy. So now I'm going to look at the sites where my height exceeds 1. So why does this not percolate? Well, if I use bk plus non-coexistence, I know that it's impossible that h bigger than 1 and h smaller than 0 percolate. Right, so maybe here it's h bigger than 1. And then here maybe I have some component which is h less or equal than 0. And I know that they cannot percolate at the same time. But if I look at h less or equal than -1, this is clearly a subset of h less or equal than 0. But those two are equal in distribution. Okay? So clearly, if I look at h less or equal than -1, then this is a subset of so it's impossible that they both percolate, but if this one percolated, then this one also percolates, and therefore this one also percolates. So this is the proof. So of course, h less or equal than minus 1, does also not percolate. Okay? So is there a question about this step?
Why the minus 1 would percolate at the same time as, I mean, why do you say it would percolate h less than minus 1?
Well, we know that this one, those two cannot simultaneously percolate.
Yeah.
So at most one of them percolates. Suppose that this one percolates, then this one also percolates by symmetry.
Yeah, but not simultaneously.
Yes, but in fact, by percolate I mean with probability 1. Because in this, we are in the ergodic setting. So okay, so we know, in fact, we know that those two sets, they cannot percolate. So now we're going to prove a second lemma. If h is less or equal than 0, does not percolate, then h of x plus 1 is stochastically dominated by h of x minus 1. Okay? So of course this is the desired contradiction, right? If we prove this, then we're done. So what I want to show is that at this point there's a small gap between those lemmas. Here we prove that h less or equal than minus 1 doesn't percolate, but here we use the fact that h less or equal than 0 doesn't percolate. So we first prove this, but then we see how to optimize the strategy to basically make those two lemmas match. Yeah, so we're not going to do the symmetry breaking, but that is the final step. So there's a gap between the two lemmas, right? Because here we prove that this one doesn't percolate, but here we use that this one doesn't percolate. So later what we do is that we put some extra machinery, and then we adapt both lemmas, and then we will see that we have the desired thing. Okay, so this is really sort of to explain the strategy except for the final piece that we're going to put in place. Right, so I mean, morally we can think about those sets as being the same, but of course we know there's a little gap that we need to fill in later. So how does it work? Well, it kind of works in the same way as before, with the expiration. So for this lemma, it suffices to prove the following, namely that minus hx minus 1 is stochastically dominated by hx minus 1. So why is that the case? Well, h is flip symmetric. So the distribution here doesn't change if we replace h by minus h. And then we just get minus hx minus 1. So now it suffices to prove, using, okay, like very standard things, that for all k in R, and for all epsilon bigger than 0, there exists a set A such that mu of A is larger than 1 minus epsilon, and mu of the event hx minus 1 smaller than minus k intersection A is less or equal than mu of hx minus 1 greater or equal than k. So okay, by definition of stochastic domination for two random variables which take values in R, we just need to check that we have the domination between the probability that they exceed a constant, right? It's just looking at the cumulative distribution function. And now I'm also saying that if I can prove it while conditioning on a set which has a very large probability, it's essentially the same. It's just like an analysis epsilon that we like to put. And just like in the previous proof, what we're going to do is we're going to say, well, I have my vertex x. So here's my vertex x. And I have this set h, which is less or equal than 0, which does not percolate. So it means that if I take a very large box, so this is lambda, then this set doesn't percolate. So this is h less or equal than 0. X this probability is smaller than epsilon. Right? And it's just the fact that, okay, it doesn't percolate, so if we choose lambda large enough, then clearly this happens. But condition on this event I find actually that on the boundary of the loop that we explored, we have greater or equal than 1. Right, so yeah, here maybe it's less or equal than 0. Okay. So now it's basically really good because if this is gamma, then I know, for example, that, okay, let's have a look. Mu of h minus 1 is bigger than k intersection A. This is equal to, well, we can just integrate over A the shape of our contour. And here we just get mu in gamma interior h of this event. But now actually if we lift the boundary condition here, then we know that this is an increasing event. So if we lift the boundary condition, it's going to be more likely, and if we decrease the boundary condition, it's going to be less likely. So this is greater or equal than A of the same thing, but now we're pretending that we just have the boundary condition 1. But now we can just use the gradient property to see that if we decrease the boundary condition by 1, this is just like decreasing the value of h by 1 everywhere. So this is A mu gamma 0, 0, hx greater or equal than k. So this is for one side of the equation. And then for the other one, we can basically do the same thing, but then the only thing that changes is that here we get the inequality in the other way because it's a decreasing event. Right? So we get mu of hx minus 1 intersection A. Oh, minus, so. less or equal than minus k, intersection A. This is equal to okay. And now, again, h tilde is bigger than 1. So we're going to decrease it to 1, which decreases this... wait, it needs to be the other way. Yeah. So we're going to decrease the height function. And because it's an a decreasing event, we're going to increase the value. So it's mu gamma 0, 1 of the same thing. And then we're just going to use the gradient property to say that this is equal to, if we put a 0 boundary condition. So it's hx minus, less or equal than minus k. But now, in fact, those two are equal. By flip symmetry. Right? So we put 0 boundary conditions, so the probability that you exceed k is equal to the probability that you're lower than minus k. Okay. No, the definition of A doesn't change here. It's no, I mean we're applying the flip symmetry to the integrand, right? And the only thing, the integrand only has this gamma circle. So what you say is really like you're trying to find you want to find boundary conditions which are at least 1. And you see that on gamma circle, the boundary conditions are at least 1. And then this allows you to do the domination argument. So, yeah, I mean... sorry?
You only flip inside.
Yeah, yeah. So what you're just saying is, well, if I find at least 1 boundary conditions, then sort of what the excess above 1 should exceed how far I go below 1. And that is what we wrote down here, basically. Right? So it's kind of, the point is that you have flip symmetry around 0, but you also have flip symmetry around 1. But if you have any distribution, you cannot be flip symmetric around both 0 and 1. So this is where the contradiction comes from. Okay. So, in fact, we didn't use really the fact that we're maximum degree 3. And we also didn't use our condition on the potential. So at this stage, we really considered, well, you could do all of what we did now, you can also do on the square lattice, and we'll give you exactly the same. So now we really need to use our inputs to prove that, in fact, you can use, you have the delocalization. So now we're going to consider mu times independent edge percolation with 1/2. So they're just coin flips. And we define, so let's call it HC. And we're going to define the following percolation. We define omega of xy. Right, so the coins, they are in 0, 1 to the edges. The omega value of an edge is the sine of hx plus hy plus the coin minus 1/2. Okay? So you can kind of, basically what we're doing here is the following. We look at the sine of the average of the two heights, but if there's a tie, then our coin flip is going to the side. Okay? Claim. Then omega equals plus and omega equals minus. Do not percolate. So why do they not percolate? Well, in fact, insertion tolerance you can prove the same way as before. And in this case, the two distributions are the same, right? I mean, the definition is completely symmetric. So what we need to show is that you can apply this, this phase coexistence theorem. And why can you apply it? Well, if you're on a degree 3 graph, so maybe this one is plus, and this one is minus. Then if I have two complementary percolations, edge percolations, they cannot cross. Or said in a different way, we can look at the following graph. The vertices of this graph are going to be the edges of the original graph. And we say that two edges are neighbors if they share a vertex, right? So this edge, this is kind of in C. Right, so if you have the hexagonal lattice, then the graph that you're going to get is this graph. And this is also a planar graph. Right, so you can see the edge percolation on on this hexagonal graph. You can see it as a side percolation on this other graph where it's still planar. And therefore you can apply this phase coexistence result on this other graph. Okay. So this is a slightly stronger version of the lemma that we showed before. Now I'm going to define a third measure. So it's mu times p1/2 edge times p edge tau, where tau is the following value. It's going to be 1/2 times e to the minus v of 0 divided by e to the minus v of 1. So in fact, sorry, it should be, I think it, yeah, it's e to the beta. Okay. So for this to make sense, beta, I mean, you cannot have an edge percolation with a parameter bigger than 1, right? So this has to be smaller than 1. And this is, of course, equivalent to our condition that log beta has to be smaller than, wait. Okay. Beta has to be smaller than log 2. So now basically when you run your exploration process, we are going to use this extra stuff to introduce some extra objects. Suppose that you have an edge where there's a 0 on both ends. Then we always call it excited. And in fact, when you are excited, you get an extra internal spin. Which is decided by this coin flip. And, okay, if you're an edge with a 0 or a 1 next to it, then you call it excited. So, okay, maybe we call this pair, we call it H coin eta. If eta xy is 1 and the internal spin is equal to 1/2. Okay. Then there are more definitions, but maybe I'm not going to explain it today. But I want to basically explain the following fact. The model somehow doesn't really, in the end we want to prove that you can find boundary conditions at the height 1/2. Of course, at the moment that doesn't mean anything because we can only encode boundary conditions at like integer heights. But what we want to say is that, well, if you have a 0 edge, then you can have this internal spin. And what you want to say is, well, I'm not going to directly explore the height on the other end. Right? Here we're just going to say, okay, I want to see the next height, I want to see the next height. But now we're going to ask first, okay, I know my height here. I want to explore this height, but first I'm going to ask if it's excited or not. Now, if it's excited, then it has this internal spin associated to it. And you can ask, is the internal spin plus 1/2? Now, it turns out that in this setup, so I think I will show it at the beginning of next lecture. In this setup, if the internal spin is plus 1/2, then you kind of kill the potential. And you're certain that here you're 0 or 1. But you don't have a weight associated to it. So in the end, this exploration allows you to terminate as follows. You know that on the boundary, either you find a height which is strictly positive, or you have sort of killed the weight associated to the edge, and you know on the other end there's 0 or 1. And when you find this, you have flip symmetry around 1/2, and then you can basically proceed as before. Okay, so I'm going to stop here, and thank you very much for your attention.